In this video, I'm going to go over the process of connecting your existing Verilog program to the Caravel Harness. We're going to do this video in two parts. The first part is going to be the user project example. We go back here to the drawing. Eventually, your user project example is going to be inside user project wrapper. The second video is going to discuss how we take everything that we've done in user project example and map it to user project wrapper. There are some assumptions that we need to make in order to have this work. First, we need to assume that you have Caravel running and that you've properly installed. And one way to check this is we do lspdk root, and that should bring up our Global Foundries process development kits. We will be using GF180 MCU-D. We should also be able to look at open lane root, and that works as well. The other thing that we need to be absolutely certain of is that you have deleted the files out of the GDS folder. That's this one here. The reason why we need to do that is because if you push the same GDS files that were part of the example, then it will not pass the multi-project wafer test. So the way you do this is you CD into the GDS folder. I don't have anything there because I've already done it. But in the event that you do see files, do rm star and it will delete both of them. Since I don't have either, it will say that I can't do anything. Then go back up one level. So when you do these directions, you should be in the Caravel user project folder. The other assumption is that you have your working Verilog. When you do this, you need to know precisely how many input wires and output wires you have. Our limitations on our project mean we can have a clock and a reset, and then we have to have no more than 16 bits of input and no more than 16 bits of output. It's going to be really important that we keep track of that in this step. In this case, I'll say we have width -1 down to 0. In this case, width is 8, so I have a total of 8 bits of input. And then I have here 2 8-bit buses for address and write data, so I have 16 bits of output. And we have a clock and a reset signal. It's important that as you're working through this, that you are diligent, take a few seconds, double check everything before you start going into the process of compilation. I'm going to do the exact same thing as I am editing this file. If you're in Word, you can open up your File Explorer, and the way that I'm able to get to my file is we go to this PC, C, and users, and then I click on my username there. And then this is where, if you're in Windows, you'll be able to go to your file. In this case, Caravel User Project. The simplest way you can do this is to do present working directory. If you're on a Mac, you can follow everything from here on down to find your file. So what I'm going to do is I'm going to go into Caravel User Project. Then the next thing I'm going to do is I'm going to go into the Verilog folder. Now you'll notice here that we are now in the exact same location as we are on the terminal. So I'm going to go into Verilog and then go into the folder RTL, Register Transfer Language. In this step, the only file we are going to modify is User Project Example. We're going to edit with Notepad++, and you're going to notice that this is the same file that if you go here in the directions, you see we have, these are the Verilog files that I pressed LS on. So if you open these, you'll notice here that these are the same 5 files. And we need to open this, and we see that this is the same file, if we click here, that you cloned from the repo. What I'm going to do next is I'm going to walk through each step deliberately so I can show you precisely what you need to do in order to ensure that you properly map your inputs and outputs and clock and reset signal to the user project example. So first I'm going to get rid of this, and you can add your own comments at the top, and I can go like this here, modified by Matthew Morrison, date 12/4/2023, email matt.morrison@nd.edu. This file contains the modified user project example provided by EFabless for connecting to the Caravel harness. Right. So there's my comment. I can add that in there, and I'm just going to press Control S to save for now. So here are my directions. So I have these 13 steps, and I'm going to walk you through them step by step. The first thing I say is to go past the inputs to the module user project example for now and go to the internals. After wire reset, delete everything except end module in user project example. So here's what I mean by this. In this file, notice here I say wire reset. We skip past the inputs. So everything I have highlighted here is an input up to this semicolon. After wire reset, we're going to want to delete everything here. So I'm going to select everything up until end module. And that's what that direction here is. Except end module. So don't delete that. Leave that there. So now we've completed step 1. Step 2, delete the existing counter Verilog module. Delete everything except default net type wire. I'm going to scroll down to the bottom of the file, and you're going to notice at the very end we have this default net type wire. Do not delete this line of code. But we want to delete everything else between end module here. So we want to delete this counter module, including end module like so. Because we are going to eventually put our own module in there. Step 3, copy your Verilog in between end module and default net type. So everything that goes here, what I currently have as line 50, is going to be our verified MIPS. So I'm going to copy everything here in this file, Control C, and paste it here. And so we're good. So those are all the various modules that we have in there. And the crucial one we're going to come back to over and over again is MIPS, because that's going to be our top level module. So that's here. This is going to be our top level module, and we'll be referring to this input early and often. So now that we're back here and we have performed this step, copy your Verilog, the next thing we're going to do is step 4. Go back to the inputs of the module user project example. Delete everything between, in this case including WBS STI and input 63 to 0 logic analyzer or LAB OENB. Also delete the IRQ signal. So here's what I mean by this. Notice here, here's WS-STBI. I say including. So delete this, and the last one is LA for logic analyzer OENB. That's this part of the direction. Delete all of those. Do not delete the IOs. And the second part of the direction is also delete the IRQ signal. And there we go. Next step. Step 5, change the number of bits for IO in to the number of input bits. Excuse me. So what does this mean? Notice how in the number of inputs bit for MIPS, I only had 8. Remember, I had 8 input bits for mem data, and then I have 16 here total for output. So one way you could do this, if you want to hard code it and you never plan on changing it, is just changing this from 7 down to 0. That gives us 8 bits. Another way we can do this, if for some reason we wanted to change this, is we could change this to width equals 8, comma, bits equals 16. And now what I can do is here I have width minus 1 for IO in. And that counts for all of the bits, save for clock and reset. Do not count clock and reset in those. The next step is change the number of bits for IO out to the number of output bits. And I say for this case, if you have 8 bits of outputs, change it to output 70 IO out. In this case, notice how I have 16. 8 goes here, and remember that in Verilog, this also ties to the next one on the line. So in this case, it's 16 total, and one way I could do this, it would just be 15 down to 0. But notice I have bits here as a variable, so I can also change this to bits minus 1 to IO out. And we will eventually, in later steps, map the 8 different bits back to this output. The next step, in step 7, is to change the number of bits for IO OEB to the number of output bits. So it's going to be the same value. So whatever you have here for IO out, keep the same for IO OEB. And IO OEB, it performs controls so that data can be read from the memory device, which basically means that we ensure that we will be able to read from the outputs. And that's going to be the step that we perform in step 10. But let's focus on step 8. So at step 8, it says you will very likely have a clock signal. In the internal of the module, set wire clock equal to WB clock I. So let's go back here. Wire clock is equal to WB clock I. That is this variable here. We're going to see the same thing, except this time we're going to negate the reset. And that, what I just did, is step 9. In step 10, I want you to use this exact line of code. So let's copy it, and then I'm going to paste it in there, and then I'll explain to you what this line of code does. What this code is doing is it is ensuring that all of our outputs are always on. So I'm going to even put a comment here, set IOEB, Control Z on that, set IOEB to 0 to ensure outputs are always on. Let me end the comment. Now add another mapping, clock, and reset wires. Okay, so now that we have this here, that is step 10. Step 11 is going to be the most complicated and important step. So make sure that you do it slowly. Feel free to press pause in the video. Make sure you double and triple check what it is you're going to do. It states, create wire buses to map to the output. So what does this mean? Well, we are going to have 2 separate wires here for address and write data. And we're going to make this the same width here. So in this case, width is 8. So I'm going to say output wires to output signals. And so I'm going to say wire, in this case, width minus 1 down to 0. So that gives me 7 down to 0. And I'm going to call this adder out. And then I'm going to do the same thing because the reason why I'm doing that is notice here that's the first adder. And then I'm going to do the same thing for write data, and I'm going to call that write data out. So wire width -1 down to 0. I'm going to call this write data underscore out. So you want to double check. So I'm going to double check. In this case, I'm going to check that width is 8. So this should be 7 down to 0. So we have 8 bits. Adder out. And I'm going to map this to my first output logic bus. Then the next thing, wire. Again, I'm going to check to make sure these are the same size. Here, this is width. It's this per module only. The reason why we know it's the same is because I have the same variable name, but that's the scope there in module MIPS. So write data out has the same one. So double check. Always make sure that in outside of the inputs that you have a semicolon after each line as well. Okay, last thing, before we actually do the module itself, I'm going to map the wires to the I/O out. And so I have 16 bits, so I have 15 to 8 and then 7 down to 0. And this helps because I have bits is 16. So this is going to be bits -1. 8 is width to width, and then width -1 to 0. So draw this out if you have to on a piece of paper so you make sure that everything is mapped appropriately. And here's what I'm going to do. I'm going to use the keyword assign and then I/O out. So we're mapping I/O out. And so I'm going to say bits -1 to width is equal to adder out. And then I'm going to do the same thing, assign I/O out. And I'll say width -1 down to 0. And that one is going to be the other one, which is write data out. So map these out based off of your widths, and you will be able to eventually map it back out to this signal. And this one is assigned here, so that makes sure that it passes. The very last step is to map to MIPS itself. So one thing that I like to do, I'm going to copy this, and I'm going to put this in the middle here, and I'm going to show you how we can ensure that we have everything appropriate. So first, get rid of the keyword module, and I'm going to press tab over here. Then ditch the parameters, because the parameters are the scope of the module definition itself. And then we're going to call it, I'm going to call it the MIPS. Next thing, I'm going to go like this, and I'm going to change it to each line. So I'm going to have enter. And then the first thing we do is we get rid of the input logic, and I'm going to do, you put a period in front of the variable itself. So it's clock, that's the corresponding input. And then we map it to the input we want from the module. So clock, this case, dot clock corresponds to this guy. And here, we're going to correspond here, up here to line 29, to clock. I'm going to press enter. Reset is the second input. That reset, and this is going to help you understand the difference in the event that you need to review. Notice how this one is RESET. This one is just RST. So you can tell that we are putting it in here. And you might recognize when you wrote in C++, this is meant to mimic the your compiler with your compiler inputs. Next thing, mem data is the input here. So I'm going to do mem data, and that is going to correspond to IO in. In this case, I'm just going to do width -1 down to 0. That's going to, I know it's the entire thing, but let's say you need to split it up. Let's say you have 16, and say you've got bits. You can do that same pattern that we did here to split up your inputs two separate buses or even more than that, depending on how you need to do it. So I'll put that comma here. And now we can get rid of mem data there. Next one is adder. So I'm going to get rid of this, put a period in front of that. And adder is going to correspond in this case to adder out. And then last but certainly not least, write data. I'm going to put a period in front of that. And then I'm going to put parentheses after that and to write data out here. I'll just move that there just so we can see that they're in the same place. So this is the main idea. You have all your Verilog here. We know it compiles because you tested it. You were able to use Virtuoso and Innovis and all the cadence tools to be able to verify this. So that's all good. We just make sure, double check that you did not delete default net type wire. That should be the very last line of code. Make sure you did not delete IF define use power pins, because that's important to get the power to everything. You should have, if you used a clock and a reset, you should have those. You should have the correct number of IOs. So in this case, I know that I have 8 bits and I have 16 bits of output. So that's input, output, and then OEB should match. I know that bits is 16, 15 down to 0, 15 down to 0. I have verified both of these. Width -1, in this case, width is 8. I've now checked that as well. I checked to make sure that the inputs to the module are surrounded by parentheses and a semicolon. And then I check the clock. I check the reset. I check every single time that I have a semicolon. I make sure that I assign IO OEB to single B0, set them all to 0. In this case, I had to separate out my 16 bits of inputs into 2 8-bit buses. So that's the first one, and that's the second one. So width -1 to 0, width -1 to 0, check, 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 it's still 16. Then I just double check, clock, reset, mem data, address, write data, clock, reset, mem data, address, write data, and then I make sure that I have the right signal. So here, this was clock, I have it to clock and clock. Reset is the input to MIPS, there it is, and I've mapped it to RST, which is there, that's exactly what I want. Mem data, I have IO in. This case, I use all 8 bits, but you can split those up. Let's say in theory, I needed 3 down to 0, and then I have other in, and then I could say, let's do 7 down to 4, 7, 6, 5, 4, and then we'll do IO in 3 to 0. So I've now split it up into 2 inputs. But that, I don't need to do that, so I'm going to change this back to width -1, 0, and put a comma after that. It's important that all of them except the very last one has a comma, so now it works. And then the last thing I check to make sure I've assigned both of them in the exact same way. In this case, I have 15 down to 0. Bits -1 is 15. Width is 8. So 15, 14, 13, 12, 11, 10, 9, 8. That is 8 bits. We are good. And that goes to address out. And then 7 down to 0. We also know that's 8 bits. And that goes there. So notice how I'm checking through this every single time, even though in this case I have this as a prepared solution, because I want you to see the process that you should use before you start compiling. Okay, last but certainly not least, notice how this is red. That means I haven't saved it. So let's save it. Now that I have that done, the other step that I need to do is we're going to compile the user project. Now, one thing I want you to do is I want you to go into CD open lane, and I want you to go into CD user proj example. And we're going to notice here that we have several different files, and we are going to open up config.json. The one thing that's important for you to check, so we're going to go to vim config.json, and I'm going to press I here to insert in the case that's different. In this case, it's correct. It is critical that your die area be 0028001760. One issue that comes up is sometimes the die area is too small and it screws up the synthesis flow. So now I'm going to get out of this and I'm going to go up 2 levels, and now I'm back in Caravel user project. So now what we're going to do is we are going to check to see if this compiles. The way we're going to do that is we're going to run the command make user proj example. And the way it works is that we have this in Caravel user project, and you run the command make user proj example. And so I'm going to talk through a couple of messages that are going to come up, and then I'm going to speed up significantly speed it up so you can see what will happen when it runs properly. So the first thing you're going to see at some point is some sort of number of warnings, usually right after this LEF files corner, so library exchange files. And in this case, we have 14 warnings and 0 errors. And what's going to happen is that you're going to run through a few steps here. Usually on step 4 or 5, if you have a specific Verilog error, it will come up here. What I'm planning on doing is I'm going to collect a standard set of common errors. The most common things that will come up is if you have too many bits in one direction or you don't have them properly mapped. If you get those kind of error messages, just double, triple check, and then go to yourself or go to a TA or myself to make sure that it's working properly. So what I'm going to do is I'm going to speed up through this, and then when I get to the end, I'm going to show you the generated GDS file for this. All right, and now we're done. We see that we have success flow complete. If you're watching this, and as I was speeding it up, you may have noticed that a few steps, particularly step 39 and step 42, took a lot longer. My project is likely going to be bigger than yours because I have the full RISC processor. So yours might not take as long, and that's perfectly fine. So the next thing we need to do is now we're here, and we need to run that same command. So if you recall from when we were in we're going to run this same command that we did a little earlier, so I'll make sure I copy it down here. But notice we have GDS user proj example, so I'm going to copy this, and we're going to do the same thing from earlier. So we're in that same folder. Notice how we go up, we get the PDF libtech, and then I press enter, and now it's going to run klayout. So here is the full design, and you can kind of already see that a lot of the design is kind of focused here over on the right, but we can make this even clearer. We scroll down here and we start getting rid of these. First of all, if we do view, we got show layers with fill, show layers without fill. But we start getting rid of all these ones here. So we double click it, fill 1, fill 2, fill cap 16, fill cap 32. And now we can actually see a large portion of our circuit. So even though, so I'm kind of hovering over with the mouse, we can see how everything's starting to get laid out in different portions. And we see our full circuit design. So we're going to close this out. That's a sign that we have completed the step. And now we're going to move on to the next step, which is mapping to the user project wrapper.